Okay, hopefully you have practiced some of the entropy calculations, looking up the values in the data booklet and then just doing those calculations where we have the sum of the entropies of the products minus the sum of the entropy of the reactants when we're at standard conditions. Also, I'm hoping that you're feeling pretty confident in predicting when reactions would have an increase, a positive entropy versus a decrease or a negative entropy by looking at the number of molar particles and the states of the reactants and the products. What we're going to do now is quickly relate the idea of entropy and enthalpy together. So when we talk about entropy, we often talk about the entropy of the surroundings. And we've mentioned this quote before that says, as time moves forward, matter and energy become more disordered and the total entropy of the universe increases. Naturally, processes will spontaneously move towards a disordered state. They will have a positive entropy. We have seen some processes that appear to occur and occur spontaneously, however, that have a net zero entropy change. This, however, can be explained when we discuss changes to entropy within a system versus the surroundings. Okay, so when we talk about total entropy change of a reaction, we need to think about how the entropy of the surroundings has changed as well. So if we look at this reaction, which is the single displacement reaction between zinc and copper, we can see that we have copper and zinc solid going to copper solid and zinc aqueous. This reaction has an enthalpy of 217 kilojoules per mole that is exothermic, but the entropy of the reaction will approximately be 0. If we think about this though, the simple change in the molar number of reactants and products is not the only thing that is going on. It is an exothermic reaction, so heat is being released into the surroundings. This is looking at simply the system or the reaction that is occurring. If we take into consideration of the surroundings, we know that heat is being dispersed into the surroundings. And we said that a change in temperature that increases the temperature will always result in a positive delta S. So this means that the entropy of the surroundings is increasing. So overall, we haven't broken the laws of physics, that the entropy of the entire surroundings, the universe, will increase, even though the entropy of that specific system is decreasing or staying at 0. So a change in entropy of the surroundings is always proportional to the delta H or negative delta H of the system. So we can say that the delta S of the surroundings is proportional to negative delta H. Exothermic reactions are generally more common than endothermic, and this is because they result in a positive entropy change in the surroundings. Okay, the heat is given off to the surroundings, so they increase the entropy of the surroundings. So as surroundings, the delta S increases, the negative delta H will also increase. If the surroundings are hot, then a small amount of added heat will not greatly affect the disorder, and it's opposite if the surroundings are cold. Okay, so we will see a greater increase in entropy if the dependent on which way our temperature change is going. So a change in entropy of the surroundings is inversely proportional to the absolute temperature change. What this means is what we are doing is deriving a mathematical equation. Using the two relationships, we can say that delta S of the surroundings is equal to negative enthalpy over T, and T must be in Kelvin, remembering our units were joules per Kelvin for entropy, and this is going to mean that we need to be dividing by Kelvin on the bottom. For a spontaneous process, the total change in entropy from a reaction, delta S total, is the delta S of the system plus the delta S of the surroundings, and this will be greater than 0. okay, for a spontaneous process if we take into consideration both the system and the surroundings. If we bring these two together, then the total change in entropy is the change in entropy of the system minus delta H of the system over T, which will be greater than 0. For an endothermic reaction, we have seen that there are some spontaneous endothermic reactions. In order for this to be possible, the same relationship must hold, that the total entropy of the system, okay, is equal to the entropy of the system minus its relationship between enthalpy and temperature, so minus delta H of the system over T. And this is going to be greater than 0. So if the surroundings are losing energy and hence becoming more ordered, in order for the relationship to hold, the system must compensate for the loss and disorder, i.e. it must result in a large amount of disorder within the system. And we see that because a lot of the spontaneous endothermic processes that we see go from a low order to a high order, from a solid to a gas, or from a solid to a dissolved salt. So when we apply the second law of thermodynamics, we need to consider the whole universe, the system and the surroundings. Order can increase in one area, but at expense of greater disorder elsewhere. So for chemical reactions, we cannot look at delta H or delta S alone to decide if a reaction will be spontaneous or not. Okay, so enthalpy and entropy alone will not determine the spontaneity of a reaction. And this is where we will move on to talk about Gibbs free energy and how we can predict and use these together to predict the spontaneity of a reaction. So that ends our discussions on entropy. I know these last few slides are probably a little bit confusing, but essentially what it comes down to is that if an endothermic process is spontaneous, then it must be increasing disorder within the system if it's taking energy out of the surroundings. Okay, if you make sure to make note of any questions or things that you're struggling with, and we'll discuss these in class.